Okay, today in this video I am going to talk about how to do ANOVA analysis for completely randomized design. Before going to ANOVA, I think it is better to identify what is the completely randomized design. Completely randomized design, as abbreviation, it can be called as CRD. Completely randomized design is one of the mostly used statistical model in researches. So, for applying this model, there are some requirements. The most first requirement is there should be only one factor that is affecting the observations other than the random error. For explaining this, I will take an example. Imagine that we have 5 nitrogen fertilizers. We need to evaluate which is the best nitrogen fertilizer that is giving highest harvest from among those 5 nitrogen fertilizers. In that case, I am going to plan a research to find what is the best nitrogen fertilizer which is giving the highest harvest. So, I have 5 nitrogen fertilizers. I am going to notate those 5 fertilizers as N1, N2, N3, N4 and N5. Okay, now I have 5 kind of nitrogen fertilizers. So I am going to apply these individual fertilizers for 25 plots which have same kind of plants and same kind of conditions. So I have applied each fertilizer for 5 plots, and then we have 25 plots which each 5 plots were treated as one of the fertilizers I have above mentioned. In this display you can see that there are 25 plots. Each fertilizer has been allocated 5 plots in randomly. So, then we can finally measure the harvest of each plot, and we can evaluate which plots are giving more harvest, that lead which fertilizer is giving the best harvest. In that case, we can find what is the best nitrogen fertilizer among the fertilizers we have applied. In such kind of researches, we can use completely randomized design. For getting much more simplest, for applying completely randomized design, there should be only one affecting factor on observations. That affecting factor can be called as the treatment. In the previous example we used 5 nitrogen fertilizers. So those nitrogen fertilizers could be considered as the treatment in the previous experiment. So if we consider the previous point, for applying completely randomized design, observations means harvest, should be affected only by treatment other than the random error. In the previous example, the harvest from each plots were only affected by treatment or type of the fertilizers other than the random error. In such situations, we can apply completely randomized design. For applying these, the other requirements are all the experimental units should be homogeneous. Before going to that point, I think it is better to identify what is an experimental unit. Experimental unit is the smallest unit that each the treatment is applied. As to the previous example, we applied each of the nitrogen fertilizer for same kind of plots. So such a plot could be considered as an experimental unit. In this display, there are 25 plots. These 25 plots were treated by using one of the nitrogen fertilizers. So each of these plots can be considered as experimental units. So one plot is an experimental unit. So I think you have understood what is an experimental unit. So applying this complete randomized design, all the experimental units should be homogeneous. That means all the experimental units should be identical other than the random error. In this example, all the plots should be identical. That means only the fertilizer, type of fertilizer can be differ other than the random error, and all the other factors such as type of soil, amount of water supplied for each plot, like those, all the other factors should be identical for each of the plots we are going to use in this experiment. For applying this complete randomized design, the other requirement is replication. Replication means each treatment should be applied for experimental units more than once. In this display, you can see in one fertilizer is applied for 5 plots. In here you can see, in this plot N1 fertilizer is applied, in here N1 fertilizer is applied, in this plot also N1 fertilizer is applied, in here. There are 5 plots among 25 all the plots. N1 fertilizer is applied. So N1 fertilizer is having 5 replicates. Furthermore, if we consider N3 fertilizer, here for this plot N3 fertilizer is applied, in here also N3, in here also N3, in here. When we consider about N3 fertilizer also, there are 5 plots N3 fertilizer is applied. So N3 fertilizer is also having 5 replicates. So I think you have understood what is a replicate means. Replicate means each treatment should be applied more than once for experimental units. We are going to apply this replication for reducing the random error. When you are looking at the model, you can understand how we are going to reduce the random error by using the replicates. Okay, this is the statistical model we are going to use for completely randomized design. In here you can see this is the statistical model, that is Yij is equal mu plus tau I plus Eij. In here Yij means the observation for ith treatment and for jth replicate. I will explain by using an example about this. Okay. In this model, the next part is mu. Mu is the grand mean. Then the other part is this one. This is treatment effect. Tau I means treatment effect. Then the other one is Eij, that is error part. Okay. According to this, each observation is affected only by treatment effect and the random error. That is why I called previously, for applying complete randomized design, the observations should be affected only by the treatment effect and the random error. Okay, now we can go for ANOVA analysis. Before going to the ANOVA analysis, I think it is better to understand how to give notation for in the ANOVA table. Okay, in the previous example we have used 5 nitrogen fertilizers. In this table you can see there are 5 nitrogen fertilizers, N1, N2, N3, N4 and N5. Each of the fertilizer had been given for 5 plots. That means each of the fertilizer had been allocated for 5 plots. That means each of the fertilizer is having 5 replicates. So N1 fertilizer is having 5 replicates, N2 fertilizer is having 5 replicates, N3 fertilizer is having 5 replicates, N4 fertilizer is having 5 replicates, N5 fertilizer is having 5 replicates. Okay. As to the model, you can see Yij is equal mu plus treatment effect plus error. So I am going to define what is Yij. As to this table, you can see Y11. Y11 means the objective for the first treatment and the first replicate. That means this is the observation for N1 fertilizer replicate 1. In here you can see Y42. This is the observation for N4 fertilizer replicate 2. Now I think you can understand what is Yij. Yij means individual observations. Okay, to do the ANOVA analysis, you have to do these calculation before going to the ANOVA table. I will explain one by one how to do these calculations. Okay, first one is Yi dot. In this table you can see these are the 5 treatments N1 to N5. These are 5 replicates for each of the fertilizers. N1 has 5 replicates, in 2 have 5 replicates, in 3 have 5 replicates, in 4 have 5 replicates, and in 5 have 5 replicates. Okay, now I am going to teach you how to calculate yi dot. Okay, yi dot means the total of I treatment. That means if we consider this one, the total of this means y1 dot. That means the total of the first treatment, the total of the N1 fertilizer, that is 144 and 0.1. Then if we consider y2 dot, we have to get the summation of these observations under N2. If we are going to calculate y3 dot, we have to get the summation of all these observations. That means we have to get the summation of all the observations under N3 fertilizer. This is y4 dot, that means get the summation of N4 observations of N4 fertilizer. This is the y5 dot, that means get the summation of all the observations under N5 treatment. Okay. Now I am going to teach what is yi dot j. Y dot j means the total of jth replicate. That means if we have got an example as y dot 1, y dot 1 means the total of observations under replicate 1. That means the total of these 5 observations. If we are going to take y dot 2, that means the total of observations under replicate 2. The total of these 5 observations. If we are going to take y dot 3, that means the summation of the observations under replicate 3. So, if you are going to take y dot 4, that is the total of observations under replicate 4. Y dot 5 is the summation of the observations under replicate 5. I think now you have understood what is yi dot and what is y dot j. Then the next part is yi dot bar. Yi dot bar means the average of ith treatment. If we are going to take an example, y1 dot bar means the average of the observations under the N1 treatment. So we can take the summation of these observations, and that summation should be divided by number of replicates under that treatment. So this is the y1 dot bar for the N1 treatment. If we are going to take the y4 dot bar, so we have to take the summation of these observations, and that result should be divided by the number of replicates. Then we can have this result. So we know how to calculate yi dot bar. Then the next one is y dot j bar. Y dot j bar means the average of jth replicate. As an example, we can have y dot 1 bar. We can calculate that by getting the summation of these observations. That means we can have to take the summation under replicate 1, then the result should be divided by the number of treatments under the replicate 1. So we should get the summation of these 5 observations and should be divided by 5. If we are going to take y dot 5 bar, we should get the summation of these 5 observations and should be divided by number of treatments. So get the summation of these observations and should be divided by 5. So I think now you know how to calculate the average under each treatment and under each replicate. Then the other important notation is y dot dot and y dot dot bar. If we consider y dot dot, that means the grand total. Grand total means the summation of all the observations. In this table we have all the observations. If we are going to get the summation of all these observations, that is called as the grand total, that is y dot dot. Next one is y dot dot bar, that is grand mean. Grand mean means the average of all the observations. So we can calculate that by getting the summation of all the observations and then the result should be divided by the number of observations. In here we can take the total of all the observations that should be divided by all number of all the observations. So this is the total and that should be divided by 25. So this is the grand mean, that is that can be written as y dot dot bar. So you know how to give the notation for this kind of a table. So if we know this kind of notation, we can go for the ANOVA table. This is the ANOVA table for completely randomized design. In previously I have said that there are only 2 factors that could be affected the observations in completely randomized design. Those are treatment and error. So those 2 factors are under source of variance. In completely randomized design, the source of variance are treatment and error. In here you can see this is the total variance. In that case, for treatment, the sum of p square can be calculated by using this equation. The degree of freedom for the treatment can be calculated by using this equation. If we have the sum of p square treatment and the degree of freedom for the treatment, we can calculate the mean square treatment by using this equation. Then for the total variance, Sum of square total can be calculated by using this equation. Degree of freedom for the total can be calculated by using this equation. If we have calculated sum of square total and the sum of square treatment, we can calculate the sum of square error. Sum of square error is equal sum of square total minus sum of square treatment. We can't calculate the sum of square error directly. That's why we are going to calculate sum of square error after calculating sum of square total and sum of square treatment. Then we can calculate the degree of freedom of error by using this equation. In here, T means the number of treatment, R means the number of replicates. So, if we have the sum of square error and the degree of freedom error, we can calculate mean square error. So now we have mean square treatment and the mean square error. Then we can calculate the F ratio for getting a conclusion for our experiment. F ratio can be calculated by using this equation. Mean square treatment should be divided by mean square error. Then we can have the F ratio for our observations. So this is the ANOVA table for completely randomized design. In this case, I am going to explain how to calculate each of these parts in ANOVA table. First of all, we can see how to calculate sum of square treatment. Sum of square treatment can be calculated by using this equation. In this equation, the first part is this. Summation of yi dot square divided by r. Yi dot means the summation of each treatment. In here, we should get the square of the summation of each treatment. In here, you can see this first part can be calculated by getting the summation of y1 dot square plus y2 dot square plus y3 dot square plus y4 dot square plus y5 dot square, and the result should be divided by r. R means number of replicates. In here, there are 5 replicates, 1, 2, 3, 4, 5. So, the result should be divided by 5. Y1 dot means the total of these observations. Y2 dot means the total of these observations. Likewise, we can take the summation of each of the treatment and we should get the square of each, the total of observations of each treatment, and get the summation. That result should be divided by number of replicates. Then the second part of this equation is y dot dot square divided by rt. Y dot dot means the grand total. Grand total means the summation of each of the individual observations. So we will have to take the summation of each of these observations, and then we should get the y dot dot square. Y dot dot square means square of the grand total. We can have the grand total by getting summation of each of the observations. Then result should be square. Then that result should be divided by RT. R means number of replicates. T means number of treatment. In here there are 5 replicates, there are 5 treatments. Then R into T is 25. In this example, first part is this one. Y1 dot is 144.1 into 2 then the summation for second treatment and should be get square. Then third observation, this one, the square, fourth one, fifth one. All the total should be squared and get the summation should be divided by number of replicates, that is 5. Then you will get this answer. That is the answer for first part. Then we should calculate this one. This is the square of total observations and should be divided by RT. The summation of these all the observation is this one and should be squared, and that should be divided by RT. R is 5, T is 5, then should be divided by 25. Then this is the answer for this part. So sum of square treatment is equal this minus this part. So that is 838.6. Then we have calculated the sum of square treatment. Then we have to calculate the degrees of freedom for treatment. Degrees of freedom for treatment is T minus 1. T is number of treatment. In here there are 5 treatments. So number of treatments is 5. 5 minus 1. So degrees of freedom is 4 for the treatment. Then we can calculate mean square treatment. Mean square treatment is equal sum of square treatment is divided by degrees of freedom for treatment. So sum of square treatment we have calculated. Then that answer should be divided by degrees of freedom of the treatment. Then we can have mean square treatment. So now we have completed this part. Now we can calculate sum of square total. This is the equation for calculating sum of square total. Sum of square total is equal to summation of yij squared minus y dot dot squared divided by RT. Yij means the observation for individual experimental units. So in this part what we have to do is all these observations should be squared and we should get the summation. Each of these observation should be squared and get the summation. Then you will get the answer for this first part. This one we have calculated previously. So we can get the summation of all the observation squared. Then this is the answer for that one. Then this part we have calculated previously. Then we can calculate sum of square total. That is this answer. So we know now we have sum of square treatment, degrees of freedom for the treatment, mean square for the treatment. Now we have sum of square total as well. If we have sum of square total and the sum of square treatment, we can calculate sum of square error. Sum of square error is sum of square total minus sum of square treatment. So we can calculate sum of square error if we have these two values. This is sum of square error. Degrees of freedom for the degrees of freedom for the error can be calculated by using this equation: t into r minus 1. T is number of treatments, r is number of replicates. So number of treatments 5, number of replicates 5, 5 minus 1 is 4, 4 into 5 is 20. That is the degrees of freedom for error. So now we can calculate the mean square for error as well. Mean square error is equal sum of square error is divided by the degrees of freedom error. Now we know sum of square error and degrees of freedom error. So by using this equation we can calculate the mean square error. So now we have all the calculations required for calculating the F ratio. F ratio is mean square treatment is divided by mean square error. Now we have mean square treatment and mean square error. So we can calculate the F ratio, that is 15.4 for this experiment. Okay, now we can go for the conclusion. Before going to the conclusion, we have to think about the hypothesis. There are two hypotheses, null hypothesis and the alternative hypothesis. In this experiment, the null hypothesis is the mean value of the harvest of each fertilizer is equal. The alternative hypothesis is at least two means of two fertilizers are different. At least the harvest of the mean value of harvest of two fertilizers are different. That is the alternative hypothesis. So resultant F value is 15.4. Then we need the tabulated F value, the population F value, to compare and to get the conclusion. This is the F table. In here we have the degrees of freedom for treatment and degrees of freedom for error is 20. So in here degrees of freedom for treatment is 4 and degrees of freedom for error is 20. In that case we can get the tabulated F value according to these degrees of freedom, that is 2.87. So resulted F value 15.4 is greater than tabulated F value. That means we can say the null hypothesis can be rejected at the significance level of 0.05. Null hypothesis is rejected means there may be a significant difference between two mean values of applied treatments. So we can reject the null hypothesis. This is all regarding how we are going to calculate ANOVA table for complete randomized design manually. If we have rejected the null hypothesis, we can say that at least the mean value of two treatments are significantly different. So Now we have to find out which means are different. In that case, there are several procedures could be followed to find out that. I will explain in another video about those mean separation procedures.